Happy Friday, everybody. Nice to see you. Hope life is going good. Missed you on Wednesday. I hope that the combined and Dalton Law lecture went well on video. You got to peek at my house and animals if you watched it as you were supposed to. My hope is that the topics from that lecture, well, they should have all been revisit. However, I know a lot of your school years ended differently last year due to COVID. So maybe it wasn't the revisit experience it should have been, but really the gas laws AP unit is scattered full of revisit stuff because there's several pre-AP topics that College Board will ask about. So you should recognize some stuff today too, alongside the brand new stuff. As my announcement said earlier this week, the solids and liquids retest takes place on Monday. So if you qualify for that retest, make sure that you are preparing over the weekend. Overall, the test grades on that exam were very good, as they usually are. One reminder though, or really just bit of advice, my fear is always that when y'all do really well on an exam, that those topics are going to become less important in your brain. Like the biggest bummer in the world is for you to have made an A or a B on the solids and liquids exam, and then the AP exam asks you a question about like covalent network, something very simple, and it's fallen out of your brain because you're worried so much about acid-base titrations or whatever. So make sure that even though sometimes we label things as easier to understand, that you keep it highlighted as important in your brain so that you don't have a real sad moment. As we continue gas laws today, you do need a calculator. Please get out a calculator and your mole fraction slides that you've already copied. So there's a lot of cool little things we can do while we play around with gases. For example, a thing I would have showed you last lecture had we been hanging out was a demo on Lussic's law. If you remember, Lussic's law is going to be the relationship between pressure and temperature, claiming that they're directly proportional. What one does, the other does the same thing. So my tube here is full of gas, all right, and then it's got a liquid added as well, but we can show Lussic's law by heating up the gas on the inside. So if I use the heat from my hand to make the temperature go up on the inside, the pressure will go up too, and I can make the liquid get quite reactive. All right, I'm not squeezing or anything. It's made of glass. I would break it. All right, and then if I let go, you'll see that it chills out. All right, but then we can just heat it right back up on the other end, and as I do, you can make it go crazy. Another very minor thing, playing around with gases. I've got now an empty. Dang it, I meant to do that last period. It's not gonna be good if it's wet. We'll try anyway. I have an empty vessel here. I can get it clogged with a ping pong ball, and then I've got my little suicide bomber button over here. I'm just kidding. But if you take the button and I push it, it sends a spark into the vessel. Now, right now, there's nothing in the vessel, so you'll see that if I push it, nothing happens. But if I take some of this liquid here, I know we're not studying liquids, but I'm going to tell you about it. But if I take some ethyl alcohol, let's get it added. There we go. Okay. All right. So if we add some ethyl alcohol to my vessel, well, this liquid right here is very volatile. And if you remember the word volatility, you might remember that it would be described as being a very fast evaporator and quite combustible, meaning that it will react with fire violently. So what's happening right now while I have the vessel plugged again is that the volatile alcohol that I've added to it is evaporating very quickly because that's what it does. Therefore, it's turning into a gas. I'm going to add some mechanical energy here. And the gas form of it that we have now trapped inside the vessel is going to have similar properties to the liquid version, meaning it's going to stay combustible. And while this isn't anything that's going to make your mind explode, I can make the ping pong ball be a bit more entertaining because now there's a gas trapped in here that wants to react to the spark. And if we go in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, boom, suddenly it's a lot more fun. And it happened pretty quick, so just kick it this way when it makes it a bit. You probably couldn't see it because it was so fast, but there was a purple flame on the bottom of the combustion, so it was extra cool. But anyways, if that wasn't the most impressive thing that you've seen, I do want to let you know that on Wednesday of next week, which is our third lecture, I am planning on blowing something up. It'll take place outside, so all you remote kids will get to go outside with us. I can't do it inside because they get mad at me if I burn buildings down. But weather permitting, we are planning on having a little bit of fun before Wednesday's lecture. Now, I say weather permitting because water is the driving force in the reaction that I'm going to do. You can only add exactly 2 drops of water. I mean, you can add more, but it just gets more violent. So if it starts raining, we'll just all die. So anyway, hopefully the weather's nice on Wednesday. You ready? We're going to continue our stroll through gas law topics, just showing you different things that might be thrown at you. So here's a new one that you probably have not seen before called mole fractions. A mole fraction is actually exactly what it sounds like it would be. You know what a fraction is, a part over a whole. So a mole fraction of gases is going to focus on one gas that is part of a mixture of gases and figuring out what fraction it makes up. For example, if we were to simplify the gases that you're currently surrounded by, I would say that you have oxygen, nitrogen, and carbon dioxide surrounding you. What if I wanted to find the mole fraction of carbon dioxide in that mixture? Well, here's what the expression would look like. All right, so we would say X, because as the slide says, a big X is associated with mole fraction of CO2, because I'm picking the carbon dioxide, is going to be equal to the moles of CO2 over the moles of O2 plus CO2 plus N2. All right, those three, because that's what I said in my example, the mixture of the room was made up of. So it's the part that we were studying over the whole of all the gases present would equal the mole fraction of the carbon dioxide. And then you could add in values or whatever. Now, hopefully that's easy to understand since it's pretty much just defining what a fraction is. More commonly, though, you're going to see it associated with Dalton's law. If you remember from Wednesday, Dalton's law was a look at finding total pressure of a system while considering all the partial pressures that are making up that system. And when you consider that with mole fractions, you get this equation. Now I know it appears that there are two equations there, but it's really the same equation twice. I've just manipulated it because the only type of things I've seen them ask for mole fractions is the partial pressure referring to the mole fraction or the mole fraction itself referring to the system. So I've just rewritten the same equation twice, but realize that of course the big X is the mole fraction, and then we've got partial pressure of a certain gas, and then the total pressure of the system. So if you know how to access these two equations, the use of them is very plug and chug and simple. So let's make sure that we're all right with it, and we will work with a couple mole fractions. Let's do the top one together. So I can tell right away by looking at the first problem that I am solving for the partial pressure of a gas. Why? Because if you look at the question, it says calculate the partial pressure of nitrogen. All right? So the equation that I will choose to use is the one solving for the partial pressure. The values themselves are very straightforward. You'll see that the mole fraction given is 0.7808. While the total pressure that's given is standard at 760. I get 593 torr. So torr is the pressure unit used here. I want to point out, in case you missed it in the Wednesday lecture for any reason, that we've got our common pressure units over here, all right? Atmospheres, millimeters of mercury, torr, and kilopascals. However, that lecture left off the conversion factor for kPa. So if you would add 101.3 as kPa's conversion factor. 101.3. You probably remember that slide 1 on Wednesday's lecture listed those conversion factor values. You don't have to memorize them. They're just useful in converting between pressure units. But I left off kPa at 101.3. Take 2 minutes and solve the other one. It's ridiculously easy if you figure out what it's looking for. Take 2 minutes and find the answer to the second question. should have been straightforward because the question's asking for the mole fraction. Therefore, it's our formula here where the numbers are provided. I do want to point out, though, that the mole fraction does not have units. We've dealt with this before with things like K values in equilibrium. There are no units for mole fraction. .210. Our next topic is the major revisit for the day, because hopefully the ideal gas law is something you've seen before. There will definitely be at least one AP question covering it. So let's make sure that we are still really good at Pivnert. A couple important things that I want to mention about Pivnert. First off, I want you to understand the analytical difference between it and the combined gas law from Wednesday. The combined gas law, the P1V1 over T1 equals P2V2 over T2, is a before and after look of a gas situation. That's why the ones and the twos are there, right? It gives you a scenario. It says something like the temperature goes up, and you have to track what everything else will change to. The ideal gas law is not like that. Instead, it's just a snapshot of a gas as it exists. You'll notice that Pivnert doesn't have ones and twos because there's no alteration of scenario here. It's just taking a look and analyzing a gas as it exists. I also want to point out that the units for the ideal gas law are highly specific, and that's because we are using a constant value R in the calculations. If you look at that slide, that constant number R that you don't have to memorize, it'll be given to you. The units are liters atmospheres over moles Kelvin, which is dictating all of the other units that must go into the equation. I don't think you'll have any issues with moles and Kelvin because your brain should already be trained to get rid of degrees Celsius, and moles is moles. But the liters in the atmospheres you've got to be careful of, all right? We usually measure milliliters in the lab, so that's usually what's given. So you need to convert it to liters. And then pressure can go all over the place. So you got to make sure that only atmospheres goes into any equation utilizing R. So let's have our big revisit moment and make sure that we can do Pivnert right here. Let's analyze this gas situation, and I'll start by extracting the numbers. All right, it looks like we've got 0.46 moles. And 33 degrees Celsius. And 9.5 liters. I always like to also add a question mark to the bottom of my list because I know that it will be asking for something. My equation is up here, so let's go ahead and match units to variables. Moles is units of N. Degrees Celsius is units of temperature. Liters is volume. And the question says, what pressure? I can see that there's no repeat in units here, which is a good indicator that the combined gas law is not being used. Therefore, an R value will also be needed. Which of course is 0.0821. Plug and chug into Pivnert. All right, we don't have a pressure. Our volume is 9.5. Our mole count is 0.46. R value 0.0821. And careful, our temperature is given in degrees Celsius, right? The volume was good because liters is what we want, but the temperature is no good. So add 273 to get to Kelvin. I get 1.22 atmospheres. Now, there's several different angles that I've seen questions asked that have you use these different gas ideas. So I'm just going to show you examples of each of them, and then Schoology will give you some good practice. So one of them is a look at gas density. Now, of course, we already know about gas density. It's the lowest, has the lowest density of any of the states of matter, right? But sometimes you're going to be asked to use a calculation on gas density. And that's why I want you to see this guy here. This equation is not given on your AP sheet. Instead, it can be derived from other equations put together. You can do that, but it's hard. Harder anyways. I suggest memorizing this equation so that the moment a density or a molar mass of gas shows up, you can recall it and quickly tackle it. The way that I memorized this equation when preparing for my certification was this. Any of y'all own a cat? You got a kitty cat at home? All right. You know how after it goes and uses the litter box, it does that scratch thing with its paw? So here's what I see. I see that if you turn this second M upside down, it becomes a W, which makes it say meow, of course. And the meow puts the dirt over its pee. Yeah, right? Yeah, meow and dirt over its pee in the litter box. Anyway, that's how I remembered it. But the use of it can help you solve different types of equations. So let's look at a couple different applications of this gas density equation. I'm going to work these both with you. Now, the first question seems real simple. Calculate the density of oxygen at STP. Let's talk about that a little bit. All right. STP is standard temperature and pressure. It was referenced last lecture. And it gives values that you don't have to memorize, but you need to know that you've got to go look them up if you can't remember that the standard temperature and pressure is 0 Celsius and 1 atmosphere. But it wants to know the density of a gas. So I'm going to use our new equation here to do it. It's analyzing oxygen, right? Oxygen is, of course, O2. Therefore, from that expression, that formula, I already know the molar mass. I didn't tell you to get out a periodic table, so you'll have to take my word for it on a couple of upcoming problems, unless you want to go get a periodic table. But O2 has a total mass of 32. All right, so I know this variable then. Let's see if I have enough other information to find density. The molar mass of 32 equals the density, I don't know that yet, times R, 0.0821 constant, times temperature. Now remember, STP, the standard temperature, is 0 degrees Celsius or 273 Kelvin. Over the standard pressure, 1 atmosphere, that's nice. So now, careful with your density units there because we haven't used this in a long time. But remember, density is mass over volume, so grams per liters. The next question is a bit more cross-cutting in regard to pulling up an old topic, and this is a common way for them to connect all of this together. So focus in so that you can see how we tackle this next problem. All right, so it says here's a formula, CHCl. All right, we've got the formula CHCl. And it wants to know what is the molecular formula of a certain sample of this gas. Well, that's an empirical formula, right? Because an empirical formula is a formula with the most reduced ratio of subscripts. It wants to know the molecular. So there's some stuff that we can do here. Now, I know that the key to finding a molecular from an empirical is molar mass. That's the big deal, which is why this equation, since we're dealing with a gas, looks really useful because molar mass can be really helpful in figuring this out. Let's see if we have enough of the information to find the molar mass of this gas sample. Well, we need a density, and we're not given a density. But I know that density can be found as mass over volume. And lucky for us, we're given a mass of the gas of 0.8 grams. Over a volume of 256 mils. Now careful, because density, just like R, doesn't work with mils, works with liters. We need liters divided by 1,000. All right, 0.256. And I have a density value that will be useful. Let's find the molar mass of the gas we're analyzing. The density is 3.1. The R value is constant. The temperature, if you look, hey, it's given in Kelvin. That's a rare gift. We put the dirt over the P. Ruh-roh, we have an issue with the pressure. There's an R value here that requires atmospheres, but the pressure's given in torr. Lucky for us, it's a simple one-step conversion that you might have already peeked at. Which, of course, to go from torr to atmospheres, there's the given value. The diagonal will match units. Here's the conversion factors from slide 1 of the previous lecture. And my conversion gives me 0.99 atmospheres. So let's find the molar mass. And I get a molar mass of 96. Of course, we still have work to do for the answer because the answer is a formula, right? It wants a molecular formula of this green guy here. So now let's think back to, well, how do I find a molecular formula from this kind of data? All right. Well, there's the molecular mass. What we need is the empirical mass. We need to compare the mass of the empirical to the mass of the molecular, meaning we need to add up CH and Cl. So the CHCl, carbon, hydrogen, and chlorine on the periodic table has a molar mass of 48.47. The way that we, if you, I hope, remember, find the molecular formula is we will take the molecular mass divided by the empirical mass, and you always get a whole number to multiply the empirical by. If I multiply the empirical by 2, I get a final answer of C2, H2, Cl2. How are we doing? A little blast from the past there. Lastly, one more little angle is gas stoichiometry. Another cross-cutting idea where we can bring the analysis of gas into a reaction where we're comparing the amount of reactants to the amount of products, which of course is stoichiometry. Now, one nice thing that I notice about this problem is that A, the equation's already balanced, which is required, and B, it only gives us information on one of the reactants, meaning that limiting reactant is not a part of the analysis. All right, we don't have to figure out which reactant is winning. We're just going to analyze the water producing hydrogen in this reaction. So here's what I see by looking at the question. It wants volume. Make sure that you agree. All right. It wants volume, but we are not, it's not at a standard temperature. So we have to use one of our gas equations to give us volume. And the only one that will help us here is going to be the ideal gas law. Therefore, I need the components of pivnert in order to find volume. We're analyzing the hydrogen product, but we only have the water reactant. So I need to turn the water reactant into hydrogen product stoichiometry. But we don't want the units to be grams, because look at pivnert. Pivnert doesn't use grams. It uses moles. So let's put all that together on the board. The given value of our reactant is 98.3 grams. So I've got 98.3 grams of water. All right? And we're trying to get volume of a gas. So I don't want grams. I am trying to turn it into hydrogen product. All right? So I need to get over there. Now, I have to first go from grams of water to moles of water, because we can only convert reactants to products by going moles to moles. That's a stoichiometry basic. But once I have moles of the reactant, I can go to moles of the product. My diagonals will match. the non-numerics, of course. All right, so some stoichiometry now. Whenever moles and grams are compared, the conversion factors is 1 mole equals periodic table grams. So we add up the molar mass of water, which comes out to 18.02. Whenever moles is over moles, that comes from the coefficients of the balanced equation. So go and look, and you'll see that they are both 4s. Now that I have moles of the gas that I'm analyzing, finding volume is easy. Pivner, here we go. The pressure, look at the problem, is 0.98 atmospheres. The volume is what we're going to find. The moles is a calculated 5.46. R is constant. I wanted to go 1, 2. And the temperature is 450 degrees Celsius plus 273, of course. Questions?